Many of the projects described above developed robotic cold bending techniques for exploring complex and large space frame structures, compared to cold forming a bend in a rod from the above projects. This paper presents a robotic hot bending system that locally heats the rod and bends it into a curved shape within a transient moment. Moreover, the research project not only takes advantage of an induction heating technique to develop a non-standard robotic bending system, one able to produce and customize various continuous curves with less machine power needed, but also aims to demonstrate and examine this novel technique by fabricating a large wire mesh structure to be assembled with each specific metal rod as case studies. The system consists of two main components, a 6-axis KUKA industrial robotic arm with a pneumatic clamping gripper as an end effector, and an integrated fabrication platform for feeding, heating and cooling. The integrated fabrication platform includes an induction heating machine, a metal rod feeding machine, 2 cooling fans. In this test, metal rods with diameters of 4 mm, 6 mm and 8 mm were heated and manually bent to validate whether materials with different diameters could be heated and bent, after a series of tests. In consideration of machine performance and the material's constitutive property, 6 mm was chosen for further use in this experiment. In the material test, the metal rod hovered after it was heated and bent by a heater. Material was still heated but not hardened. The metal rod then deformed and fell due to either external force or gravity. To solve this problem, after the metal was heated and bent, a radiator fan was installed in the base frame to cool down the bent metal, and at the same time a waffle plate with the same height as the bending point was installed in the base frame to support the heated metal rod to ensure the accuracy of the bent metal. For accurate control of the bending angle at each and every bending point, we selected 3D models for bending into 3D curves. Next, we disassembled all such 3D models using Rhino and Grasshopper software. Then, each curve was equally divided in order to calculate the precise position for the robot to bend the metal. The description of the arithmetic process is: firstly, an anchor point in the material conveyance mechanism was designated and a bending point in the center of robotic pneumatic gripper was selected. The distance between both points was measured. The conveyor had to move the metal rod forward to the same distance each and every time. Secondly, each and every curve acquired by disassembling the 3D models was equally divided. The length acquired from the division was treated as the distance between anchor point and bending point. Next, the perpendicular frame was placed on the equal point, and the tangent vector acquired from the curve and equal point was treated as a reference vector. The z-axis of the frame was aligned with this vector. The robot's bending position was found using the changes of movement of the frame pairs on the curve. Lastly, the robot's bending positions and the corresponding digital output signs were integrated into a sequence. This sequence was then converted into KUKA robotic source code using TACO. For safety reasons, a collision detection mechanism has also been added to the program. This research aimed to represent a complex surface with non-planar contour curves to examine the accuracy of our three-dimensional metallic rod bending method. This approach may assist in overcoming the difficulties of building a substrate system when constructing curved walls. Our overall geometry was a single patch of a gyroid 135 cm wide by 100 cm depth by 200 cm high, which is a triply periodic minimal surface that was discovered by Sheng in 1970. In this case, the gyroid unit is formed by 8 patched surfaces with 3-fold rotation symmetry, and each gyroid unit is able to infinitely connect to others. The selected single patch of gyroid is firstly sliced into regular and grid curved networks via the contoured component of the grasshopper. 18 curved segments in each x and y direction of the surface. Based on these 18 curves, 2 variables of the contour component are manipulated to generate a weaving pattern. For assembly, the curves of the surface are classified into 2 groups, edges and contours. The edges are labeled from E1 to E6, and the contours are labeled by the direction of division, either from X1 to X18 or from Y1 to Y18. 1. A frame structure as bounding box is built to temporarily support the rods. Based on this supporting frame of 6 rods, curves on the edge of the surface are placed and fixed to the corners of the frame structure via zip ties. For the sake of verifying the end vertices of each contour, the curves are placed in the proper position along the edges of the surface, intersections between the edges and the contours of the surface, and labels are marked with tape on these edges as a reference position. With this layout, 2 selected contour curves, with the largest span being across the surface in the X and Y divisions, are placed to ensure that these 2 contour curves are intersected and set on their edges. After positioning these 2 longest pieces, the rest of the rods are sequentially placed in the right position and temporarily fixed to the intersection between the 2 contour curves by using zip ties. The last step is to weld all the intersection nodes and remove the frame structure. The following pictures shows the final results of utilizing this hot bending procedure. Overall, this research exploits the differential material states of metal, computational tools, and advanced fabrication technologies to discover a unique digital workflow of a metal bending technique. Based on a series of experiments, the project successfully achieved a robotic rod curving system for the development of an intricate metal wire sculpture on a 1:1 scale. Unlike the cold bending method, this paper demonstrates a robotic hot bending procedure that shapes straight metal rods into 3-dimensional curves. However, the current system is limited to bending each segment to a maximum of approximately 70 degrees. In addition, the fabrication process is a semi-automatic, robotically bent, manually assembled or manually welding. The output of a bent metallic rod is manually supported to prevent any angle deviation that might be caused by the weight. Further research in this area will require adjustments to the current bending system and the development of an algorithm to improve the maximum bending and accuracy of the angle. The development of robotic assembly and welding system to improve the fabrication efficiency.